Okay guys, so this is stereoisomerism in complexes, and there's two types of stereoisomerism in complexes. There is geometric isomerism, also known as cis-trans or EZ, and there is optical isomerism, and we're talking about both of those today. So the first thing we'll do is geometric or cis-trans isomerism, and there's two shapes of complexes which you need to know about in terms of cis-trans isomerism. The first one is an octahedral complex, and this is using monodentate ligands. What I mean by monodentate ligand is a ligand that only donates one lone pair of electrons to form one dated covalent bond, or sometimes they're called a coordination bond. So like quilt and duvet, two separate words but they mean the same thing, and dated covalent and coordination. So what I'm going to do is, it's octahedral. I know that because it's got 6 ligands bonded to it, 6 monodentate ligands. So I'm going to draw out my shape of an octahedral complex. When you're drawing these wedged lines, do make sure you shade them in. If I left this unfilled, it would actually mean a dotted line. So if I draw 2 dotted lines and 2 unfilled lines, I'm essentially drawing 4 dotted lines, which is obviously wrong. So do make sure you shade these in. It takes like a second. And I'm going to draw my second octahedral shape, just like so. In terms of cis-trans, all you need to do is this. With, well, which one should we do first? Let's do cis first, and then we'll do trans afterwards. With cis, both of my identical groups point in the closer direction. So I'm going to have one H2O at the bottom here and another H2O on the side there. So you can see they're almost pointing in the same direction. Also notice I made sure it was the oxygen that was connected to this bond, not the hydrogen. It's the oxygen that donates a lone pair of electrons, so that needs to be the one on the bond. If I did this, what I'm actually saying is it's the hydrogen that donates a lone pair of electrons. And obviously hydrogen doesn't have a lone pair, so it couldn't possibly do that. So once I've drawn my 2 groups facing in the same direction, I just add on the other 4 to the other 4 bonds. So I've got NH3 4 times. Again, I'm going to make sure the N is attached to the bond. And that would be my cis isomer. For my trans isomer, all that you need to do is make sure your 2 identical groups point in the opposite direction. So the way I always remember this is just by putting one on the top and one on the bottom. So I've got a H2O on the top and a H2O at the bottom. And I'll have my NH3s on my other 4 bonds. Now this, at the moment, each of these diagrams would have lost me a mark. Have a think about why that is. Everybody always forgets this. And what it is the charge. This complex has a charge of 2+, so I need to remember to draw my 2+ charges on. And now that's a fine answer, that's a good answer. So cis, they're both pointing roughly in the same direction, one down and one sideways, but trans, they're both pointing in opposite directions. And we can use this same thing, same technique, for a square planar molecule. Now there's not very many square planar complexes that you need to know about. Definitely the main one is platinum. Now platinum is a platinum molecule with 2 chlorides and 2 ammonias bonded to it. So cis, they're both pointing in the same direction, so I'll have both my Cl's pointing like that, pointing upwards, and my NH3s pointing downwards. With trans, I would have them pointing, my identical groups, pointing in opposite directions, so I'm going to have one Cl here and one Cl there. And my NH3s would also end up pointing in opposite directions. What a lot of people do for cis and trans is this. So we've drawn our cis. For trans, okay, I'm going to do the opposite to that, so I'm going to have both my Cl's on this side. Can you see how this is still a cis? This is not trans. All I've done here, look, here's my 2 Cl's, I just turned it on its side. So these 2 are identical molecules, but just imagine twisting your head like that. So you can't make that mistake. You've got to put them on opposite bonds. So one Cl there and one Cl here. Will do nicely. Okay, so that's geometric or cis-trans isomerism in monodentate ligands. What we've also got though is bidentate ligands. The definition of cis-trans isomerism is molecules with the same structural formula. Look, here's their structural formula, it's the same, but a different arrangement in space, or in 3D space. What everybody always says for this is it's molecules with the same molecular formula. Well, yes, they do have the same molecular formula, but also they have the same structural formula, and that's what you need to say. So the same structural formula, but a different arrangement in space. Look, these are arranged differently in space. So what we're talking about now is bidentate ligands. Bidentate ligands are ligands that donate 2 lone pairs of electrons to form 2 dative covalent or coordination bonds. And a really good example is ethanoic acid. Just like that, that's a bidentate ligand. Each of these O- can donate a lone pair of electrons to a central metal atom. So what we're going to do is iron we'll have 2 of those, and we'll have 2 Cls. Now each of these has a charge of 2 minus. There's 2 of them, so that equals 4 minus all in all. 2 times 2 is 4. Your Cl has a charge of 2 minus, so that would equal a total of 6 minus. I'm going to give my ligand total charge of 4 minus. This tells me the charge of the ion. So I've got 6 minus here. If my total is 4 minus, this must be ion 2. My total is 3 minus, it would be ion 3. So you can figure out the charges of your metal by looking at all the other charges and realising the difference. If I knew that this was ion 2, but I didn't know this charge here, I'd do 2 plus, minus 2, minus 2, minus 1, minus 1. It must be 4 minus. Okay, so you can figure out the charges, providing you know the charges of all your different ligands. There's a really nice table in your book on that, which we'll show you. So, again, I'm going to draw this out. This is octahedral. And what we're going to do is, essentially, we're going to do cis-trans again. But this time using a bidentate ligand. So the way I always do this is, again, cis, both of my 2 identical functional groups are going to point roughly in the same direction. So I always do it 1 pointing down and 1 pointing to the right slightly. Whereas trans, I'm going to have 1 up and 1 down. So that's my, essentially my cis-trans shape. All I need to do now is add on my bidentate ligand. So I call this the propeller method. So you're going to make it look a bit like a propeller blade. So I'm going to put 1 oxygen here attached to the bond next door, and I'll just add on those double bonded oxygens, and then this oxygen goes to the bond next door as well. So you can see it looks a little bit like a propeller blade there. If you try and do this bond here, the oxygen go into there, and this oxygen go into there, it just looks really scrappy and it gets really confusing. Always make your bidentate ligand form its 2 bonds next to each other. It just makes your diagram look so much simpler. And let's not forget, again, we've got our charge. And then I'm just going to do the same here. Notice again how I'm putting it on bonds next to each other to make it look nice and simple. And that would be my 2 different cis-trans isomers. With bidentate ligands, you can also get optical isomers, and that's what we'll do now. So again, I've got my Fe, it's octahedral, so this is the same molecule. So this molecule really has got 4 isomers, 2 cis-trans isomers and 2 optical isomers. Okay, so with optical isomers, what I always do is imagine a mirror down the middle. And what we're trying to make is a mirror image of these 2 different shapes. So we had 2 Cls. I always put my monodentate ligands facing towards the mirror. Now there's many ways to do this, you don't have to do that, but I find this really works for me, so I would definitely advise doing that. So both my Cls on each side are going to face towards the mirror. I then put my first bidentate ligand on the remaining top 2 bonds, and my remaining bidentate ligand on the bottom 2 bonds. I'm going to do the same for this side. And at the bottom. And let's not forget the charges. Okay, so now you may not think that this is any different to that. You may think, well, if I twist this round, I'm going to end up with exactly the same molecule. You really have to think about this. This bond here is facing into the board. If I was to twist this round, this bond would now be facing away from the board. Whereas here, it's facing into the board. So kind of, here's my finger, this is the bond facing into the board. If I twist it round, so the CLs are on the same side, it now faces out of the board. I'm not sure if you can make this out on the video, but what I've got here is 2 models to show that. Fiddly models. Okay. So here we have, this is what I'm supposed to be showing on the board there. Here's the green ones are my CLs and the red ones are my ethyl dioic acid. Look what happens when I try and twist this round so it looks like the other one. If I twist it round, can you see how the red one's pointing in opposite directions? In this one, it's facing towards the right, but in this molecule, it's facing towards the left. So again, look like that. I'm going to twist this around. It's not the same, is it? Look, they're not the same. If I show it from the top, you can see them facing in opposite directions. Okay, so although it may look like these are identical, they're actually definitely not. And the very final thing I wanted to show you is how to draw a hexadentate ligand. A good example of a hexadentate ligand is EDTA4-. Okay, EDTA, this is a very simplified diagram. It kind of looks like this. Now that's a very simplified diagram. Obviously there's the 4-. The way you draw this round a central atom, let's just say we've got copper, is what I call the claw method. So we've got these 2 nitrogens in the middle there. I attach these onto adjacent bonds. We then make the oxygens kind of like a claw coming around it. So I'm going to have 1 O go in there, another O go in there. See how they kind of claw over the top. And then the 2 on the bottom kind of claw around the bottom there. And again, let's not forget, if it's EDTA4- and it's copper 2+, that will be a 2- charge there. Okay? Optical isomers are isomers that rotate plane polarized light. That's one of the definitions for them. So if I had plane polarized light going like this, and it went through one optical isomer, it would get rotated to one side, or if it went through the other optical isomer, it would get rotated to the other side. If we have a racemic mixture, that's a 50-50 mix, then it won't get rotated at all, because it will get rotated equally and oppositely to both sides. Okay? So you'll know if you have an optical isomer, because it rotates plane polarized light. Okay, thank you.